Welcome to Lecture 4.5, Generalized Fourier Series. I want to begin with a quick review of the main ideas from the previous lecture because these form a foundation for what we're going to do in this lecture. The last lecture was on Sturm-Liouville theory, and the main concept here was a Sturm-Liouville equation, which was a second-order ODE of the following form. Negative the derivative of p of x y prime plus q of x y equals lambda w of x y, where here p, q, and w were all positive functions. We are usually interested in solutions to this equation on a bounded interval, say ab, under some homogeneous boundary conditions. So this is like alpha 1 y of a plus alpha 2 y prime of a is 0, and beta 1 y of b plus beta 2 y prime of b is 0, and the alphas both can't be 0, and the betas also both can't be 0. So together, this boundary value problem is a Sturm-Liouville problem. We write that as SL problem. We don't usually say that. Now, one reason why this is so important is because if we divide through by W here, then we can actually write this equation here as a linear operator L times y equals lambda y. So this is an eigenvalue equation, and what we want to do is we want to find all possible eigenvalues lambda and all possible eigenfunctions y. Here's the main theorem that we learned last time. Given a Sturm-Liouville problem, the eigenvalues are all real and they can be ordered, so they are increasing and they diverge off to infinity. Secondly, each eigenvalue, lambda I, has a unique, up to scalars, eigenfunction yi. Finally, with respect to the inner product defined to be f dot g is the integral from a to b, f of x, g of x bar, w of x, that's the weighting function. The eigenfunctions form an orthonormal basis, well, they can be scaled to form an orthonormal basis, on the subspace of functions. This is just the fancy notation, say the set of smooth functions that satisfy these boundary conditions. And the reason why this is true is because a Sturm-Liouville problem is just an eigenvalue problem, Ly equals lambda y, and L is a self-adjoint linear operator. Therefore, it has all real eigenvalues and orthogonal eigenvectors. And the fact that they can be ordered like this, that go off to infinity, that's a difficult technical detail that is beyond the scope of this class. You don't need to worry about why it's true. Just know that it is. Okay, so here's that main theorem. Same thing as on the previous slide, but now I want to use this to motivate a definition. If f is a smooth function on AB that satisfies the boundary conditions, then it can be written uniquely as a linear combination of the eigenfunctions. That is, f of x can be written as the infinite sum from n equals 1 to infinity of c of n yn of x. And just like we do for Fourier series, we have a simple formula for the coefficients Cn. And this is just a projection because it's just based off of linear algebra and the simple vector space structure and inner products that we discussed in section 1. So Cn is the inner product of f and yn divided by the inner product of yn with yn. The reason why we have to divide by this is because in general, yn of x that we get need not necessarily be a unit vector. In Fourier series, we're given sines and cosines. We know those are unit vectors. But in general, when we find an eigenfunction, it need not have unit length. Now we could always normalize it, and then we have a simpler formula, just this numerator. But in general, maybe normalizing it might be messy, and we want to keep it maybe in a polynomial form as integer coefficients. And if we want to do that, then we have to divide by this yn dot yn. And let me derive where this came from. I know I've done this before. Look at, in particular, the very end of lecture 1.4, but it's worth seeing it again because it's important. Okay, so this sum, writing f of x as this infinite sum of cn yn of x, I could write this as an infinite sum, let's say n equals 1 to infinity, of an times the normalized version of yn. So yn of x divided by norm yn So I could use a different coefficient, an, and write it like this. And clearly, or I should say Cn is an divided by norm yn. Okay, so if we do this, now this is a unit vector. So we know right away that an is just the projection of f onto that unit vector, yn of x, divided by norm yn. And I can pull that norm out in front, which is just a constant, 1 over norm of yn times f dot yn. I'll just say f dot yn. So if this is an, then Cn is this thing divided by norm yn, which is f dot yn divided by norm yn squared, which is f dot yn divided by yn dot yn. And that's where this formula for Cn comes from. So another way to write this formula is with an integral using our definition of an inner product. It's the integral from a to b, f of x, yn of x bar, w of x dx. That's the integral of f and yn. And then on the bottom, we have integral from a to b. And remember, this really what this thing is this is yn of x times yn of x bar, which being complex valued functions, that's just the norm of y of n of x squared. And let me remind you, when I say norm here, I mean the complex norm, not the norm of the function. I know that's confusing. So maybe if you don't like this, you can just think of it as yn of x times yn of x bar times w of x dx. Okay, so this is a complicated formula, but this works not just for sines and cosines, but any Sturm-Liouville problem. If we can find the eigenfunctions, then we can express any solution to that equation using those eigenfunctions. And this is called a generalized Fourier series with respect to the orthogonal basis of the y's and the weighting function w of x. And when I say the weighting function, I really mean with respect to this inner product, because that inner product is characterized by the weighting function. Now, I should say, just because my conscience is bugging me a little bit, that I'm being a little bit vague when I say f of x, or a little bit incorrect when I say f of x equals this infinite sum, for several reasons. So first of all, I've just, to make things easier, assumed that f is smooth, has no discontinuities, but we could weaken this. We can weaken this to be piecewise. And if it's piecewise, and it, say on a to b, if it has like a discontinuity, then not surprisingly, just like for Fourier series, we can come up with this infinite sum, but what it will do is, at this point of discontinuity, it will equal the average of the left and the right values. So that's one thing. But more importantly, when I say f of x equals this infinite sum, I really mean that this infinite sum, this converges to f of x. And remember what it means for an infinite sum to converge to a function. That means the sequence of partial sums, Sn, converges to f. And here s capital N, and s capital N is the capital nth partial sum, so the sum from n equals 1 to big N of Cn yn of x. So this sequence of functions, this thing converges to f. And now when I say converges, I have to be careful of what that means as well, because there are different notions of convergence. These are all beyond the scope of the class. They're probably at the intro graduate level, but I think it's worth noting because we've gotten this far. And I think the best way to show you what I mean is to give you an example of a sequence of functions that converges. Actually, I'll give you two examples. That converges in one sense, but not in the other sense. So here's a function. So I'm going to define this to be f1. So this is f1. It is 1. So it's this step function. It's height 1 from 0 to 1 and 0 elsewhere. And then f2 is going to be height 2, but width 1/2. So this is 1/2, and this is 2. This is f2. And then let's go dot, dot, dot up to fn. Not surprisingly, the nth function has height n, but only width 1 over n, and then it's 0 elsewhere. And this sequence of functions, so this is fn, and the sequence fn converges to the 0 function if we're just looking at the open interval 0 to infinity, because every single point from 0 to infinity in this interval will eventually become 0 for all of these functions. So this converges so this here we mean pointwise. But this does not converge in norm to the 0 function, because the norm, let's just define the norm as the integral, the area under the curve. The norm of every single one of these fn's does not converge to the norm of the 0 function, which is 0. So this converges pointwise, but it does not converge in norm. Here's another example of this. So let's define the function fn of x to be 0 everywhere except there's this little blip from n to n plus 1. So this sequence of functions, fn, converges to 0 on the whole real line, because, it doesn't seem like it, this hump never goes away, but every single fixed point, take any real number, there will be some index where that fn of that number is always 0. So every point will eventually become 0 forever, so this converges pointwise. However, this does not converge in norm. So this does not converge, the norm of the fn's do not converge to the norm of the 0 function, because that's 0. So these are examples where we have to be a little bit delicate as to what we mean by convergence. So down here, when I say f of x equals this infinite sum, it technically doesn't equal it pointwise, and we'll see more examples of this in the next lecture because of this weighting function, but it converges in norm. It converges with respect to this inner product. Okay, that's all I want to say about this. As I said, it's beyond the scope of the class. It's at the graduate level, but since we're this close, it's worth knowing that we have to be a little bit careful when we talk about convergence. Just like in the previous lecture, we're going to conclude with 4 familiar examples that we first saw in lecture 4.1. We studied boundary value problems, and we solved these things completely. Okay, so here we have a Sturm-Liouville problem with Dirichlet boundary conditions. The ODE is negative y double prime equals lambda y, with boundary conditions y of 0 and y of pi both being equal to 0. So in the previous lecture, in lecture 4.1, we let this be L, but I'm just going to let L be pi because it just makes the math a little bit easier, because I want to make it as less notationally messy as possible. So the eigenvalues are lambda n equals n squared, and the eigenfunctions are yn of x equals sine of nx. The orthogonality of the eigenvectors, or eigenfunctions, as guaranteed by Sturm-Liouville theory, means that if you take the inner product of ym and yn, which by definition is the integral from 0 to pi of ym of x times yn of x times the weighting function, which recall is 1 in this example. So that's the integral from 0 to pi of sine of mx sine of nx dx. That's 0 if m and n are different. That's easy to check. And it's pi over 2 if m and n are the same. That's an easy thing to check, that it's pi over 2. And I will say that when we studied Fourier series, remember that we put things like a 1 over pi in front of here. It doesn't really matter how we scale our inner product. I'm leaving it like this because it's simply easier. Note that theyn's do not form an orthonormal basis because the norm of each yn is the inner product of yn with itself, well, it's the square root of that, which is the square root of pi over 2. Finally, the last part of the main theorem of Sturm-Liouville theory is that we can take any function f of x, which is continuous on 0 to pi, that satisfies the boundary conditions, and we can write that uniquely using these eigenfunctions. And that's just a simple Fourier series. We know how to do that. So Bn is the inner product of f with sine of nx over the inner product of sine of nx with sine of nx. And again, I went over in detail a few slides ago why we have to divide by this. Basically, it's because theyn's, as we have them here, sine of nx, are not quite unit length. So that's why we have to divide, we have to normalize it. So Bn is just the integral from 0 to pi of f of x sine of nx dx divided by the norm squared of sine of n of this function, which is just equal to that. And that's pi over 2. So if we divide by that, we get 2 over pi times the integral from 0 to pi of f of x sine of nx dx. And that looks like a Fourier sine series, and that's exactly what it is. Example 2. The same Sturm-Liouville equation, but with Neumann boundary conditions. So the same ODE that we've seen throughout this lecture and the last lecture, but now y prime of 0 and y prime of pi is 0. So this is a Sturm-Liouville problem. If recall, the eigenvalues are n squared for non-zero n. N could be 0 this time. And the eigenfunctions are cosine of nx for non-zero n. The orthogonality of the eigenvectors means that if you take the inner product of ym and yn, by definition, this is the integral from 0 to pi of ym times yn times the weighting function w of x dx. This is the integral from 0 to pi of cosine of mx times cosine of nx times 1. That's w of x. And it's easy to check that that is 0 if m and n are different, and it's pi over 2 if m and n are the same, assuming they're both actually cosines and not constants. It's slightly differently if one of these guys is equal to 0. In other words, if the eigenfunction is the constant function 1. And I could put that in cases, but I'm not going to worry about that because I just want to give a summary now. So once again, this means that the norm of yn, which is the square root of yn dot yn, is, well, if n is positive, it's the square root of pi over 2. And I'll leave it as an exercise to check that if n equals 0, just plug in 1 in place of cosine, that you get the square root of pi. In other words, the integral from 0 to pi of cosine of 0 times cosine of 0, or 1, is actually pi instead of pi over 2. So from the last result of the main theorem of Sturm-Liouville theory is that any function, f of x, continuous on 0 to pi, satisfying these Neumann boundary conditions, can be written uniquely as an infinite sum of these eigenfunctions, in other words, of the cosine terms. And an, as before, is the inner product of f with cosine nx divided by the inner product of cosine of nx with itself. As before, that's the integral from 0 to pi of f of x cosine of nx dx divided by the norm squared of cosine nx, which is just this. So that's 2 over pi times the integral from 0 to pi of f of x cosine of nx dx. And this is for n greater than 0. It's slightly different if n equals 0. In fact, the same formula actually holds for a naught if instead of this formula here, you say, well, let's write this instead as a naught over 2 plus n equals 1 to infinity of an cosine of nx. So that's one reason of why this a naught over 2 is in place, is because it gives the same formula for all an's, including n equals 0. And the reason why we need to do that is because of this pi over 2 versus a pi. Example 3. I think you're getting used to this now. Mixed boundary conditions. The same ODE, but now y of 0 is 0 and y prime of pi is 0. So this is a Sturm-Liouville problem. The eigenvalues are the squares of the half integers now. So n plus 1/2 quantity squared, where n is non-negative. And the eigenfunctions are the sine functions, but now the frequency is this omega, which is n plus 1/2. So sine of n plus 1/2 x. The orthogonality of the eigenvectors means that if you take any two of these guys, say ym and yn, and take their inner product, that by definition is the integral from 0 to pi of sine of m plus 1/2 x times sine of n plus 1/2 x times the weighting function w of x dx. The weighting function, of course, is 1. Let me just clarify that there's parentheses around here, and this is equal to 1. And that's equal to 0 if m and n are different, and that's guaranteed. You don't even need to check that. That's guaranteed by that main theorem of Sturm-Liouville theory. And similarly, this integral is pi over 2 if m and n are the same. That's something that you have to check. That's not guaranteed. You know that it's going to be non-zero because only the norm of the zero function is 0, but you don't know exactly what it's going to be. So as before, this means that the norm of each function, yn, which is the square root of yn dot yn, is the square root of pi over 2. Now, I don't know whether to call this a Fourier series, an ordinary one, or a generalized Fourier series, but the last part of the main theorem of Sturm-Liouville theory says that any function f of x continuous on 0 to pi satisfying these mixed boundary conditions can be written uniquely as an infinite sum of these eigenfunctions. So in other words, the sum from n equals 1 to infinity of bn sine of n plus 1/2 x. And again, I don't know whether to call this a generalized Fourier series or not because these frequencies are half integers and not integers, or not of the form n pi x over L. Whatever you want to call it, we have a formula for the bn's. Bn is just the inner product of f with the nth eigenfunction divided by the norm squared of that eigenfunction. So that's the integral from 0 to pi of f of x sine of n plus 1/2 x dx divided by the norm squared of that. Remember, the norm squared is pi over 2. So we just get 2 over pi times the integral from 0 to pi of f of x sine of n plus 1/2 x dx. Finally, we come to the last example of Robin boundary conditions. So same ODE, and the left boundary condition is Dirichlet, y of 0 is 0, but now we have y of 1 plus y prime of 1 equals 0. Here, instead of pi, I'm letting this just be 1. This is a Sturm-Liouville problem with eigenvalues, lambda n being omega n squared, where the omega n's are the positive roots of the function y of x equals x minus tangent of x. That's why I let this be 1 instead of pi, just to make this easier. And the eigenfunctions are the sine functions with frequencies omega n. So the orthogonality of the eigenvectors means that if you take any two of these sine functions with these weird irrational frequencies, by definition that's the integral from 0 to 1, because we're using 1 for our L here instead of pi or L. So it's the integral of ym of x times yn of x times the weighting function, which is sine of omega mx times sine of omega nx integrated from 0 to 1. Now that's not something that we can really solve generally, except we are guaranteed by Sturm-Liouville theory, by that main theorem, because the linear operator is self-adjoint, that this integral, this inner product, will be 0 if m and n are different. That's an amazing result. I mean, we can't do explicitly, but we know from our linear algebra theory and integration by parts that that integral is going to be 0. Now, I'm putting a question mark. We don't know what it is when m and n are equal. We don't even have closed form solutions for these roots, so we can't really come up with a closed form solution for what this integral is. We just know it's going to be non-zero. So as I said, there's not a nice closed form solution, but the norm of yn is still the square root of whatever the heck this quantity is. So now this is really a generalized Fourier series. Any function f of x continuous on 0, 1, satisfying these Robin boundary conditions. So f of 0 is 0 and f of 1 plus f prime of 1 is 0. This can be written uniquely as an infinite sum of these eigenfunctions. So the sum of bn sine of omega nx. And bn is the inner product of f with sine of nx divided by the norm squared of sine of n, not sine of nx, omega nx with itself. So that's the integral from 0 to 1 of f of x sine of omega nx dx divided by the norm squared of sine of omega nx. And so that's on the top, it's the integral, again, the same integral, f sine of omega nx, and the bottom, it's the integral from 0 to 1 of sine of omega nx squared. Okay, so we have a formula for bn, not going to be a closed form, but if you have a computer, this is something you can absolutely do. And I want to finish with a comment. Throughout I've said any function continuous on 0, 1, and I've alluded to this before, that's stronger than we actually need. We can get by with piecewise continuous functions. And if we do that, so a piecewise continuous function, anytime it has any sort of discontinuities, then this function that we get, it will actually converge to exactly this function, except at those discontinuities, it'll converge to the midpoint. Okay, so that's a good place to stop. This is a great preview for the next lecture, because the next lecture, instead of doing these familiar examples of a really simple ODE, where the solutions are sines and cosines, we're going to do examples from physics and engineering involving Chebyshev's, Legendre's, Bessel's, and Hermite's differential equations. Our solutions are going to involve power series and polynomials, and so we'll do the same thing, but our generalized Fourier series are truly going to be generalized Fourier series, because they won't even involve sines and cosines. They will involve a lot more, I want to say complicated. Actually, in some cases, they're really simple polynomials. Regardless, it's a remarkable landmark piece of mathematics and highly relevant throughout the sciences and engineering. So please stick around and stay with us.